I'm Yusheng, and today's we are going to share our reinforcement learning work on the miles, and these will introduce the A&D part. Okay, so now I give a very general ideas of the reinforcement learning. We can see overall, if you want to, let's understand what's the high-level concept of the reinforcement learning. We will let the model to roll out to exploring as small as probabilities, and let it to take the agent and get the reward and feedback from the external world, or we say the environment, and use this feedback and rewards to optimize itself. So you can see this is the ILO objective. This is what it's doing. And in the ILO training, especially on the large language model, this field, people will use like a PPO, or especially recently use the GRPO to train the model. And but when we do the reinforcement learning, you can see here, this is a simple form. We can separate the two parts. The first part is you need to allow the model to do the rollout as small as possible to exploring more opportunity. And then you need to have a very efficient training engines to optimize your model. So because of these two requirements, we will need the, within the ILO framework, we will have the training engines, and then the other part is the inference engine, and that then work together. So in the inference engine part, in the miles, we use the SGNeRM, and in the training part, we have the FSDP and the Megatron LM. So after we have these, and we still need a mechanism which is called weight sync, because once you optimize or update your weight in the training site, you need to sync this new weight to the rollout size, and allows your currently ILO can use the lattice model to do the exploring and the rollout. Yeah, but there's a problem. If you want to build the better model with the ILO training, you need to scale it up, and you will have encounter some efficiency problems. And the other one, because as I mentioned, there are two different engines in the ILO system. So you may encounter some mismatch problems, because you will use your inference engine to get some output, but your training engine is also use the different kernel or function. You will get a different output. So once you have this kind of mismatch, it may make you cannot converge, or make your final accuracy become poor. Yeah. So because of the reasons that I mentioned, in the miles, we provide a series of features to support the efficiency, and then allows our model keep scaling up the ILO training. The first one is the collocate and the disaggregate. In the ILO, and sometimes when people train the ILO, they will share a group of the GPU, and they will do the rollout first, and after do the rollout, it will release this GPU and allows the training engines to use this group of GPU. Yeah, but if you want to scaling up, we can put the training engine and the inference engine in a different group of the GPU to allow it have the better efficiency to run overall ILO training. Yeah, and we also have the fully async, which is mean because we have two different engines. So when you generate the rollout, you can still utilize your training engines to do the training. So once we can, the miles provide a disaggregate mode to allow you can deploy the training engines and the inference engine on the different workload GPU. And then you also provide the async mode to allow your overall idle trainings, the async. You don't need to wait off your rollout, finish your rollout. You can work on the next step. Yeah, and there's this and the features is not on this slide. It's in the inference part. We also have the PD disaggregate because in the SGNet we can let our prefield and the decode on the different grid over the GPU. Yeah, so this is in the rollout side. We also have this kind of optimization. Yeah, and the other part is the low precision. In our mouse, we also provide the FPA and info rollout, and you can largely reduce your rollout times. And the RDMA weight sync, these mechanisms that I just mentioned, because you need to pave the lattice model weights between the training engines and the rollout engine. And we have use the RDMA weight sync this mechanism, we can largely reduce the weight sync time. And the last one is the multi-token prediction. Yeah, these features, I think everyone's already know this. It was proposed by the DeepSeek, and we also provide these features in the miles. And in the determinism, we also have some feature to control, make our training engines and inference engines outputs mismatch these raw replay, and we even have the training inferences kernel. We have a kernel, and that was used in the inference side, and we also use the same kernel on the training side to make their kernel align, and we can guarantee their outputs are 100% the same. Yeah, and the last one is the token-in-token consistencies, because we find, especially in the agentic task training, it will make your input tokens and output tokens are different. So it will also make some mismatch and even degrade your final model accuracy. Yeah. So this is overall of our miles framework provide this kind of feature to allow your scaling up your RL training and also improve the efficiency, and at the same time also guarantee its determinism. And this is the work that we recently have done. They will support the DeepSeek v4, and we also verify our miles can work on the DeepSeek v4, conducts the reinforcement learning, and its reward can grow scalable. Yeah. And we also support the rollout part. Yeah, the rollout parts on the MI300 AMD GPU on day 0. Yeah. So this is some general idea of the miles. And regarding for the AMD support parts, these will give more example.
Thank you so much, Yusheng. So today, the full end-to-end miles pipeline already running on AMD. So our goal is not only to make it running, but also to make it more scalable, efficient, and competitive. So as we know, RL workloads rollout heavy memory bound, and it requires the very tight coordination of inference and training. So we want to optimize both sides of the system. SGLang for rollout phase, Megatron LM transformer engine for the training phase. We also enabling the key features like true-on policy, R3, and many others. Beyond the single node optimization, we also scale to multi-node in asynchronous mode. So eventually, we are building a solid roadmap to position AMD as a strong platform for RL workloads. So yeah, let's look at the rollout phase with SGLang support on AMD. This experiment is based on Qwen 3 30B A3B model running on MI300X. So if we look at the left figure, this is end-to-end decode latency. So with the optimized kernel stack, we can see speed up is like 10 to 15%. This is due to our multiple kernel updates, including like attention kernel, MOE gem kernel, and MOE routing kernel. They are all coming from our ATER library. So beyond ATER library, we also support Mori, which is a high-performance EP backend. So we'll explore this for future improvements. Major RL features are already enabled on SGLang, like R3, true-on policy, async rollout with sync, and it also enables flexible EP, DP rollout scaling. Moreover, we have a broad coverage, a model coverage like DeepSeek, Qwen, Llama, and many others. So yeah, let's go to the training side. So we mainly optimize transformer engine, which is the key component in Megatron LM. So with our latest TE version, we have two major updates. The first one is fused attention. The second one is grouped gem. With fused attention, it's using a single kernel that combines QK, softmax, and V together. It's hand-tuned on MI300. It significantly reduces the memory traffic, so especially for the long sequence calculation. For group gem, we combine multiple expert gem into a single kernel launch. Also combine multiple hip blast calls. This is super important for MOE workload because it can improve the actor train performance a lot. So with these two major updates in our latest TE, we can see it improves the RL workloads a lot. If you look at this table in the bottom, so the calculation of the computation of log probability and the ref log probability improved like 2.5 and 2.2x separately, and the actor train improvement is about 2.2x. Then the end-to-end step time, including rollout, train, and with sync, is about 1.5x. So this is a pretty big improvement for latest TE. Now, so with this major update with both rollout phase and training phase, we will see where is the time, where does the time goes to the end-to-end RL workloads. So this is the experiment from Qwen 3 30B A3B model. If you look at this pie chart, the pie chart is the step time breakdown. So we can see the rollout phase is about like half time. It's a major bottleneck in RL workload. Then the actor train is like about 30%. So it's the second bottleneck. So we also see the calculation of log prob and ref log prob. It's about like 12% in total. This is like GRPO overhead. Then lastly, the with sync is not too much, but it will be significant if we want to scale to multiple nodes. So yeah, beyond the single node optimization, we also look at the key feature enabling, including true-on policy. The concept here is very simple. So for true-on policy feature, we want to have the same token, same kernel, same weight, and it can calculate the same log probability between rollout and the training phase. But in current setup, it's not the case because our rollout and the trainer phase, they are using different kernel implementation, which means it will introduce the numerical mismatch. So eventually, the log probability computation between rollout and training, they are different, even at step 0. So how are we going to fix it? So we want to align the forward computation of training and the rollout phase together. Basically, we want to use the training phase is using the same kernel implementation with the rollout phase. In this case, we can have the same token, same weight, and the same kernel. Then we will the log probability difference will be 0. So in the bottom, this is our little experiment to show with and without true-on policy. So without true-on policy, we see non-zero log and ref log prob difference. And with true-on policy, it's all going to be 0, and we have 0 gradient bias. Okay, so yeah, beyond single node optimization, we want to scale to multi-node. So in this, we want to separate training and rollout phase into a different set of nodes, like as shown in the picture. So we have the weight sync to combine trainer phase and rollout phase. So in asynchronous mode, the rollout phase and the trainer phase, they are overlapping each other, means they run in parallel. So when our rollout phase is generating data, the trainer phase can still do weight update. However, this induces several challenges in this architecture. For example, if our rollout phase and trainer phase, they have they are imbalanced, then that will lead to GPU resource waste. Then second, the rollout phase sometimes use still weight. It will lead to off-policy drift for scaling. And third one is for weight sync, since we are now going through the network, so it will induce network latency. So with these challenges, we want to have some common sense. We will design the scaling. The first thing is we want to scale out the bottleneck phase as much as possible. In this case, the rollout phase is bottleneck, so we want to add more rollout nodes. Second, we don't want to sync weight every step. Yeah, probably we want to sync every several steps. That will reduce the time. And third, we want to optimize the rollout to train ratio to minimize the idle time. So with this setup in mind, so this is some experiment we are doing. So we use Qwen3 30B A3B model and run on 3 nodes, 6 nodes, and 9 nodes on MI300. So if you look at this scaling result, on the first row, the left side, this is the training throughput. We can see pretty linear scaling of the throughput from 32K to 67K to 105K. And on the right side, it's the rollout throughput. Similarly, we see very linear scaling of the throughput. On the bottom side, this is the log probability. This is the log prob gap between the rollout and the training. So if you see at the very beginning, because of the off-policy drift, we have a little bit gap. Then with the time, as time goes and with the model learning evolves, we see a little bit of drift. But importantly, we can tell even the drift is a little bit, but it's consistent among all the different nodes. So which means our scaling is stable. So from this experiment, our conclusion is we are able to achieve linear scaling of both rollout and the training session, and we are also able to meet the numerical stability. Yeah, with that, for next steps, since we still want to continue tuning the large-scale RL performance, not only from the node configuration perspective, but also from multiple different areas. And second, we want to enable more features. As what Yusheng just mentioned, there are a lot of like latest MIOS features we want to enable, like low precision training, speculative decoding, MTP, and the PD disaggregation, and int4. So those are all areas we will need to do more improvement. Then we are actively enabling CI/CD pipeline on AMD GPUs to have a native support of MIOS system. And lastly, but very importantly, we are continuously doing contribution to MIOS community. So yeah, if you are interested in IO workloads, just connect us in offline. So hopefully we have more discussion. Thanks very much.